So I'm Marco Passerini, and I've been working for the last 3.5 years at CSCS. My main duties are maintaining our production OpenStack system. In this presentation, I'm going to give you some more details about this infrastructure that we built in the last years, and about the upgrade operations we have been doing last winter. So let's give a basic introduction of what is cloud computing. If you look on Wikipedia, the few lines are saying that cloud computing is the on-demand availability of computer system resources without direct active management by the user. So this is really nothing new. This is pretty much the same as we are doing in HPC since many years. But what is the added value of cloud computing? So cloud computing comes with the idea that we are providing services to our users, and the community came up with different names to define the different level of freedom that we are giving to our customers. So the most common level of freedom we are giving is infrastructure as a service, which means that we let our users create their own VMs or deploy their physical bare metal nodes, get access to their storage, everything in a programmatic way. Then we have something like platform as a service, which is something more similar, like middleware as a service, software as a service. So if you think of something like an online web application like Gmail or even, for example, Office Online. So these are applications that don't need to be installed on your computer anymore, but they are accessible through the web, and they are hosted by a remote data center which has a lot of computing power. And then there is also some minor definitions such as container as a service, database as a service, function as a service, and so on. Something different from what we see in traditional HPC systems is that in cloud, usually users want to have immediate access to resources. They don't want to sit and wait in a queue, like what is happening on, for example, our Pittsdane supercomputer, where the system is very big, but there is so many jobs that the users want to run that they need to be queued with some fair sharing scheduling, and they will be allowed to run only when there is some free space for them. So when you have a system which needs to be immediately accessible, this means that the system has to be much bigger than what you are actually going to use. So the operators need to do capacity planning and forecast how the need will grow over time, and always buy hardware in advance. Also, something which is different from HPC is that in HPC, traditionally, the jobs are short-lived. In cloud, there can be short-lived jobs, but at least in our systems, we saw that we are seeing mainly very long-running jobs, which can be considered permanent, such as web applications, which are not going to be taken down if not after a few years. And having long-running jobs means that the system needs to be built in a way that you want to have the minimum amount of downtime. So you need to have HA all over, and you need to allow live migrations of VMs in order to perform hardware maintenance. And on top of this, we also have over-provisioning, which means that since these applications are not always CPU intensive, we might want to put more jobs onto a single node in order to better use what we have available. Another concept of cloud, which we often hear, is the concept of private cloud or public cloud or hybrid clouds. So what we know from major vendors such as Google or Amazon or Microsoft is that they are offering public clouds, so they are offering the service to anybody, and people just pay something to use these resources. And this is different from what is a private cloud, which is what, for example, they are doing often in the industry. So there is a big company which have their own machines, and they just want a way for their developers to do computation and development in a scalable and fast way. Another important feature of cloud computing is the accountability, especially when we talk about public clouds. So usually these big vendors who like to trace in details what the users are doing in terms of not only computing, but also network usage, storage usage, and so on. So we need to, if you want to offer a cloud service, we need to improve on the traditional billing that we have been doing on HPC, which is usually based on CPU hours. Something also which is very important in clouds is the programmability. So differently from HPC systems where people do SSH and run codes, we are now allowing users to program the systems using REST APIs. And these APIs also allow to manipulate the hardware using software-defined networking, storage, and data centers. And together with the programmability, we also have added the bonus of using modern authentication models, which allow you more easily to do federation of institutions, having multi-tenancy, so giving different levels of access to different customers. So over the last years, we have been having a few major projects which have been requiring resources from CSCS. And these are usually European collaborations, such as the Human Brain Project, which is together with Phoenix, part of the Phoenix research infrastructure. And then we have also CTA, SDSC, and Marvel. So CTA is a big telescope array, and SDSC is the Swiss Data Science Center, and Marvel is a group which is working on material science, and they are building a portal for collaboration. So usually these type of projects are requiring us to build some cloud infrastructure for them, because they want to develop new web portals which are using modern workflows, for example, using microservices. And the idea of these web portals is to act as social websites, a bit like Facebook and so on, which let users collaborate with each other and share data and run jobs in a very easy way, so that they don't need to know how to use Linux, and they can just point and click and run simulations on big systems around Europe and the world. So our solution for these customers which are asking for cloud resources at CSCS was to use OpenStack. OpenStack is a collection of many projects, open source, which was born with the idea of providing infrastructure as a service. Mainly, it started with the idea of providing virtual machines to users. And OpenStack has got a web-based interface. You can access it also from command line and through REST API. As I mentioned, there are many projects involved in the OpenStack community. There is more than 60 of them. Each of them has got a specific task. For example, Nova is the one for managing virtual machines. And we have Horizon, which is the web front end of OpenStack. Keystone is the part doing the authentication. Cinder is doing the block storage. Swift the object storage, and Neutron the network, and so on. All the way down to database as a service, or monitoring, or logging. OpenStack as a project started in 2010, and there's been since then about 19 releases. every time there is a new release, they give it a name. Usually they are named in alphabetical order, and they get the name from a city in the country where they did the last OpenStack summit. The current one we are running at CSCS is Queens. And the latest one, which will be available in a few days, is Stein, which will be presented in a few days at the next Open Infrastructure Summit. Since there are all these projects which are part of OpenStack, you can imagine that it is quite difficult to install and maintain such a system. So over the years, we have seen many deployment tools coming up. Some of them are open source, some are not. And they, in theory, should facilitate the deployment of your OpenStack infrastructure and make it more easy to do upgrades and changes to the environment without breaking dependencies. This is the history of OpenStack deployments at CSCS. So we started in 2016 with some basic evaluations using tools such as PACStack and so on. And then in 2017, we involved Red Hat. We did an initial test deployment on old hardware. And then in May, we installed our general purpose OpenStack cluster called Pollux. This system was installed in about 2 weeks with a consultant from Red Hat. And it is based on Okata OpenStack, which is following the Red Hat naming called the Red Hat OpenStack Platform 11. So basically, we have the OpenStack versions which are like Pike, Okata, Queens, and the Red Hat versions are following a numbering schema which is following the name, so 10, 11, 12, and so on. Then in August, we deployed the test system on our own without the support of Red Hat, and in 2018, we installed another system based on always on OpenStack, which is more tied to HPC. But I'm not going to tell you much about it. But basically, the main difference is that on Pollux, we are running a big scientific portals for collaboration. And on the other system called Mitten, we maintain ourselves some small HPC clusters. And we don't let the users create their virtual machines, but we just give them SSH access to these clusters as if they were normal supercomputers. And by the way, the reason we do this is because this is somehow more flexible for us to create fast, deployable systems. So when we deployed this Pollux generic OpenStack cluster, we had some requirements. So first of all, we wanted to have a tool which would simplify the installation, and we wanted to have the ability to do upgrades over time. So basically, after doing some scouting, we chose to go with Red Hat, and then we also had some other requirements, which were to integrate with our authentication system, which is based on LDAP and Kerberos. And the problem here was that Kerberos doesn't work well with the Keystone authentication system. So we had to do a workaround, and we found a tool called Keycloak, which is the open source version of Red Hat single sign-on. And we chose this tool also because it allows us to integrate our OpenStack cluster with other sites around Europe using SAML and OIDC. There will probably be a talk from one of my colleagues about it tomorrow. Then another requirement we had at CSCS was to integrate the storage with our existing SAN infrastructure. Usually with OpenStack, people install Ceph, which does not work well with SAN. Usually you install Ceph on boxes with internal disks. And so we try to integrate it with Sun. We are still doing this work because we haven't found the perfect solution yet. But what we managed to integrate with the Sun was the Swift part, so the object storage, which is based on a spectrum scale CES object, which is, as you might know, spectrum scale is what was called the GPFS. We also have integration with our tape library, so all the backups of the object storage are going to tape. Furthermore, another requirement we had was to create an isolated network for our OpenStack installation with the possibility of possibly accessing internal CSCS resources. In general, we don't allow external users to access the CSCS internal resources from OpenStack. But if there is a special need, we can do it using something called provider networks. The user networks are implemented using VXLAN. So at the moment, this Pollux system has about 300 users. It has got about 200 users and more than 300 VMs and about 42 projects. So it's quite a small system for now. The uptime has been pretty good last year. So we had about 99.93% considering the unplanned breaks and 99.7% including also the planned breaks. During the year, we had to do some big site-wide maintenance and also a couple of major upgrades. This is why we had some further downtime for planned breaks. This is how the interface of OpenStack looks like. I'm showing you only the main page, then there is much more pages that you can access to do customizations. Basically, when you log in, you have a dashboard. You can see what project you are a part of, and you can see how many instances are running in your project, how many CPU you're using, and how many RAM models you are using, and so on. And basically, from here, you can create new virtual instances. You can upload objects to the object storage. You can create networks. You can also do some things like Spark and Hadoop jobs and so on. So this is how the layout of the system is at the moment. We have one director node, which is using for installing the cluster. Then we have 3 controllers, which are in HA. And these are the ones which are running the coordination services, so for the web page and for orchestrating the creation of VMs and so on. And then we have about 25, 30 compute nodes and 3 storage nodes. So right now, the services are running inside of Docker containers. This is something which came with the latest upgrade we have done. And this is a quite modern way of running systems, because traditionally all the services were running under a systemd. But having the services inside of container makes it more easy to do upgrades and scale out the system. This is the hardware configuration. As you see, we have these 3 FAT controllers, and we have about 20 compute nodes with 500 gigabytes of RAM and 5 compute nodes with a bit more of RAM, 768. Then we have 3 Ceph nodes. This is a quite small storage system with SSD and SATA drives. And then we have 4 external object storage nodes, which are used for on top of GPFS, and they are attached to the Sun. So we can potentially extend the storage of this part of the system as much as we want, because we have a lot of capacity on the Sun. What is interesting is that we are doing over-provisioning of the CPUs, so we can run 4 virtual cores on top of each hyper-threaded core. So we are actually, since our workloads, since our workloads are not very intensive in terms of CPU, we are optimizing our space. And we're also doing over-provisioning of the RAM. So when we installed the OpenStack with Red Hat, they suggested this quite complex network solution where we have bonded interfaces on every node. They're based on 40 gigabit Ethernet. Then we have also interfaces for API access and provisioning using IPMI. And then we have all these VLANs which we had to create, which are segmenting the different networks of OpenStack in different parts so that they are secure and they don't interfere too much with each other. So we have one VLAN for tenant network, one for storage network, and one for storage management, internal API, provisioning, provider VLANs, and so on. So basically for this small cluster, we had to allocate a lot of IPs, about 4,000. We are using OpenVSwitch, which is a way to do software-defined networking. And we also decided to use DVR, which means direct virtual routing. So this is a bit special feature of our installation, because usually in OpenStack, all the network flow is going through the controllers using something called CVR. But we prefer to avoid this bottleneck and also improve the availability of our system by using DVR, which allows the VMs to route their network directly through the compute nodes on which they are running. This is how our object storage system. As I mentioned, we have 4 physical servers which are attached to SAN, and they expose on top Swift object storage, but also S3. And there is a monitoring and GUI, there is a monitoring interface on top. And we also configure the system so that we have a Swift on file, which means that we can access the objects both through REST API, but also from the POSIX file system, which is GPFS. And on the back end, we are storing data on top of flash drives. This is for the metadata part. And meanwhile, the actual objects are stored on normal drives. We are automating backups to tape. Because of our collaboration with the Human Brain project, we have a quite complicated access control list rules, so that we are allowing some people to take care of the container creation, and these people are working for Human Brain, and then they are able to grant access to other users who have a much more limited set of permissions. So in a way, we are doing something like a multi-tenancy on top of our object storage. And we've also been developing some tools to integrate CyberDuck, which is a graphical client for accessing the object storage, and to make it work with a single sign-on and SAML. So, as I mentioned before, we chose the TripleO tool, which has been rebranded by Red Hat, in order to easily install our OpenStack infrastructure. TripleO is itself a collection of open source tools, and they let you configure your system through templates and easily do upgrades. TripleO is working in a way that you need to install one director node on which there will be a full single node OpenStack installation. And this OpenStack installation will be used to deploy your production OpenStack system. And this might sound a little bit complicated, but the philosophy behind is to reuse what is already existing and don't create any new software in order to deploy OpenStack. If we look at the timeline of the support of Red Hat, we jumped into this project around this time, and we did the initial proof of concepts using Red Hat OpenStack platform version 10. But we needed some features from version 11 because of the authentication features we needed. So we had to install version 11. But the problem with version 11 is that it is a short-term support. Meanwhile, version 10 was a long-term support, which was going to be supported for more than 3 years. So this means that as we went to production with version 11, we then had to do 2 upgrades last year to move from version 11 to 12 and then to 13. Right now we are on version 13, which is going to be supported until 2022. So we are probably going to stick to it unless we have requirements of doing some important changes to our infrastructure, because there will be new features coming with the latest releases. The reason why we are preferring not to upgrade too much our OpenStack is that is because it took a lot of time to do these upgrades. So last summer we did the initial upgrade from version 11 to 12, and it took about 2 months of preparation on a test system, and then we did the upgrade of the production in about 2 weeks of work. The upgrade was done online, mostly, even though there were some major downtimes. Even though there were some minor downtimes during this operation. Last December, we did the second upgrade, and this was a little bit shorter. It took about 1 month on the test system and about 3 weeks on the production. So when you do the upgrade of OpenStack using TripleO, there are many steps that you need to follow. We can usually divide the upgrades of TripleO into groups. There are minor upgrades, which are simple package updates of the system within the single major release of OpenStack. And then there are the major upgrades which let you skip from one version to the other of OpenStack. So for example, from Okata to Pike and then to Queens. These are a bit similar in the sense that you need to first back up the system, validate that everything is working, then you upgrade the installer node, then you download the new images, and then you upgrade your templates, and then you can eventually do the upgrade of your actual nodes. So here is the flow of the upgrade. As I mentioned, you need to first upgrade your undercloud node, which is the installer, and then you move to the controller nodes and the Ceph nodes, which are upgraded online because they are built in a high available system. And then you do the upgrade of the compute nodes. But when you do compute node upgrade, you need to migrate your VMs around because you cannot upgrade a node on which VMs are running. So you need to empty first the node, upgrade it, and then move the VMs back. This allows you, though, to minimize the downtime because all the upgrades are happening. They are happening live. And at the end of the upgrade phase, there is still some scripts to run which somehow harmonize your installation. So when we moved from Red Hat OpenStack Platform 11 to version 12, we saw some very, very big changes into the infrastructure and the way of deploying the system, mainly in the configuration management part, because Red Hat has bought the Ansible configuration management tool, and now they are migrating all the configurations from Puppet to Ansible. And also, they decided to do the shift from systemd services to Docker containers. So they are basically taking the Docker containers from the Colla project and using their own tools to deploy them and orchestrate them. When you do the change from systemd services to containers, you also need to build a local registry where to download all the latest versions of the containers and from there deploy them to your compute nodes. Because of all these changes, we had to do a lot of work to modify the configuration management scripts we had. So here is an example of how the configuration worked in TripleO. So usually you have heat templates, which are then calling Puppet modules. And the Puppet modules are used to then change the configuration on the compute nodes. When we did the upgrade, this has changed because the Puppet modules are being replaced by Ansible modules. And the configuration files are deployed onto the physical nodes. And then we have the Docker containers, which are mounting these configuration files from the physical nodes. And so it's a little bit different now, the deployment flow, and many things that we had been customizing before stopped working when we did the upgrade. Because basically we had to add the new mounts to these Docker containers so that they would add our own custom configs, and we had to change the way they were going to be started, and we also had to do some changes to the health checks of the containers and so on. So during the upgrade, we saw several technical problems. Mainly we had some issues with OpenStack. We saw some freezes of the network, which was somehow happening together with the problems on RabbitMQ. And this is something that we are still working on. We have not clearly identified the reason for this. And then we also saw that for several kernel releases, we could not do upgrades to the system because DVR was not working during that period. But then we had to wait for the right fix to the kernel to come available upstream before we could do the upgrade. And also we found many issues in TripleO. For example, there were some issues with the wrong recognition of scrubbing states in Ceph, and some Ansible scripts were not totally correct, and so on. So we have been doing a lot of work with Red Hat to solve issues together with them. We've been opening many tickets and doing back and forth of messages to find what was happening. Something else which also affected our uptime during the upgrade was that during this period, it came to the public, the meltdown and Spectre vulnerability. So there were new kernels available, and the new kernels had a reduced set of CPU flags. So basically we could not do live migrations anymore across machines because we were going to moving from an old kernel which had more CPU flags than the newer kernel. And this was not working in terms of live migration. Also, when we moved to Queens, Keystone was not working anymore with version 2, so we had to do some reconfiguration to our services, especially to Swift and CyberDuck. Talking about TripleO in general terms, we can say that it's a good tool, but it is a fast-moving target. So actually doing the upgrades is not so easy as we expected, because there are so many changes to the deployment system, and you need to do really a lot of work to change your scripts and customizations to follow it. And also we had some problems with scaling the operations, because we have a quite small system, which is about 25 compute nodes. But if we had maybe 200 or 300 compute nodes, the upgrade would have been taking a much, much longer time, especially because during the upgrade from version 11 to 12, for example, the upgrade was affecting every single node at a time, and it was taking about half an hour per node, so scaling to many, many nodes, this wouldn't work. Luckily, when moving from 12 to 13, it was possible to do all the nodes in parallel, which helped us to speed up the things a lot. So, all in all, even though we had many problems, we managed to successfully upgrade our system twice, and not many sites are able to do it in place. Many scientific sites are forced to do new deployments and migrate their workloads to the new systems every time. But this is something that we didn't want to do because it was going to be pretty much complicated operation because of all the Swift data we had and the user IDs we had to migrate and so on. And basically, we managed to upgrade the production systems between a couple of weeks of work, even though we had to do a lot of preparation in advance. And also the downtime was limited to a few hours for each of the upgrades. If we look at the Swift upgrade we did, that one, it was very fast. We could do it within an hour of work. So here is a slide about the other things that we are working on at the moment on this system. So we are still trying to improve our usage of the Sun storage area network, mainly for the block storage, but also for Manila, which is the on-demand NFS service. And we are also looking at how to better integrate this OpenStack cluster with our PISDAINT HPC system. And we are trying to see how we can mount our production Scratch and project file system onto VMs in a seamless way and how to do it securely. So right now we are studying some solution, for example, NFS with Kerberos. And then we are still doing a lot of work on the authentication part. We are trying to add OIDC to our OpenStack installation, and we are also working on multi-tenancy and multi-domain possibility, because we would like to give to some of our customers the possibility of create their own users and define what resources they are going to give to them and so on. And then we are also doing some work to improve the monitoring and the reporting of our system. Something that I've been working on during the last months was how to improve the visibility for the users of what they are actually doing. So we want to let them see how much network and CPU and memory they are using, and if we can help them to improve their utilization of the system. So this is all for my presentation. Do you have any questions?